It will come as no surprise to you that there is lots of energy in the ocean. You can hear the energy in the waves crashing on the beach and feel the energy whenever you swim in the ocean as a wave pushes you over or an undertow tries to pull you further out to sea. What is more surprising is the number of ways that energy can be extracted from the ocean. Energy can be extracted from the waves, the tides, ocean currents, temperature differences, and salinity gradients. But using waves and tides are by far the most common. Sadly, although ocean energy has low life cycle carbon emissions and lots of potential, there are very few commercial scale facilities extracting energy from the ocean. As a result, ocean energy plays a much smaller role in the International Energy Agency's climate change scenarios compared with hydropower, wind and solar PV. In this diagram showing the electricity generation mix for the International Energy Agency's 450 scenario in 2040, ocean plays such a small role it's put together with other renewables. Ocean energy is still of interest, however, as it can be more predictable than the other variable renewables like solar and wind, and the capacity factor ranges from 25 to 40%. So to start with, wave energy. I'll talk about tidal energy at another time, while the other extraction methods I'm going to leave to you to investigate on your own. Interest in wave energy started in the early to mid 1970s after the first oil crisis. Over time, interest has peaked and troughed as there have been lots of different ideas about how to capture that energy. Trying to understand all the devices individually would take us forever, and it's not really useful to us. What is useful to us is to know that they can be classified by location, size, wave direction, and their working principle. Location is all about where the device sits in the ocean. If a device sits close to the shore, in water that's less than 10 meters deep, then it's called onshore technology. If the water is, say, 10 to 25 meters deep and the device rests on the seabed, then this is termed nearshore. And finally, there are the offshore technologies, which sit in water generally greater than 40 meters deep and are a long way from the shoreline. Size and wave direction is about how big the structure in the ocean is and how it's positioned relative to the waves. Technologies that use long structures placed parallel to the wavefront are classified as attenuators because they float on the surface and go up and down with the wave. The Pelamis sea snake is an example of an attenuator. Devices that are small compared to the wave and bob or pitch with the water movement are called point absorbers. These devices have an advantage over others in that they can collect energy from water movement in all directions. The PowerBuoy is an example of a point absorber. Finally, some devices are described as terminators. These are also long structures but are placed perpendicular to the wavefront. The wave plane is an example of a terminator type device. The last classification to talk about is the working principle. This is interesting because part of the difficulty with extracting energy from waves is that typically we use rotation to generate electricity. All of our turbines are designed this way. But waves have this annoying habit of just going up and down. So some of the earlier technologies tried to change the up and down motion directly into a spinning motion, but this can introduce significant losses. Some devices were successful, however, and managed to use the up and down motion of the waves to make a turbine spin. For example, using the movement of a wave to push a column of air up and down through a turbine. By placing the turbine on its side, we can see how the air makes the turbine spin. These are called open water columns and are one type of pressure differential device. Submerged point source absorbers that compress as the wave draws the buoy up and down are also pressure differential devices. Devices that float on the surface of the water, moving up and down with the waves, are called floating structures. The movement operates hydraulic rams or pumps to create usable energy. Another sort of device is the impact device. This is where a flexible structure, positioned perpendicular to the waves, moves backwards and forwards due to the wave hitting it. The last one is where waves pass over a structure and into a reservoir, and then the water is released through a turbine. This is called an overtopping device. But how do I turn all this movement into useful energy? Well, you can turn it into electricity directly through a turbine and generator, as we have discussed, or you can use the pressure from the wave to do mechanical work directly. Sort of like how a wind turbine can be used to grind grain or pump water rather than make electricity. Carnegie Clean Energy in Australia are using the movement created by the waves to generate pressure. For example, they can pressurize seawater and then send it through a reverse osmosis desalination plant. This produces fresh water without using electricity to run those high pressure pumps. Instead, they use the ocean to pump the water directly. In this way, they have increased efficiency because they are not converting ocean energy to electricity and then back to mechanical energy. But should you put your wave energy collector in the place with the biggest waves? The answer at the moment is not really. Consistent, regular, medium-sized waves are preferred. Larger waves are less predictable and more damaging to equipment. For now, we can leave the bigger waves to the surfers. Surviving bigger than expected waves is not the only technical barrier that needs to be overcome for more energy to be collected from waves. Integration into the grid is a big issue. Firstly, the challenge of actually connecting into the grids is non-trivial across such a wide space of coastline. Secondly, because we take up such a large amount of coastline, we risk damaging coastal ecosystems. Lastly, the ocean is a harsh environment, full of storms and corrosion-causing salts. So how to build these devices so that they last and how to best maintain them is still being worked on. Cost, both capital and operating, are also currently an issue for wave energy, at least in part because of the relative immaturity of the technology. It's expected that the levelized cost of electricity of wave energy will come down with time as more is learnt. But at the moment, it's hard to be sure. Government support in the way of policies and subsidies are needed to see enough wave generation installed to really understand the costs. Grid integration and cost may mean that it only has a very small part to play. Wave energy is an abundant, predictable resource with low life cycle carbon emissions. But a lack of commercial scale projects means it's hard to tell what impact it will have into the future. What's really needed for wave energy to go forward is more time in the water, more projects and more research. Only then will it be known if it's sink or swim for this technology.